Good morning, everyone. I'd like to welcome you to the second of our speakers today. My name is Anne Florini. I'm a professor of public policy at Singapore Management University. I'm also with the Brookings Institution in Washington. And as a political scientist, I am honored to be able to introduce to you one of my discipline's foremost thinkers and most creative thinkers, Robert Axelrod. But before I get into calling him up onto stage, I want to take 2 minutes to pull together a little bit of what we heard earlier this morning and the field of political science, and it's by way of a personal story, so I beg your indulgence. Brian Arthur started off this morning talking about a workshop that was done at the Santa Fe Institute about 20-odd years ago on a crude look at the whole. I was the beginning graduate student in political science who was hired to organize that workshop. That's how I got started in it. I knew nothing about any of these subjects. I just happened to know somebody at the World Resources Institute who was involved, and found it one of the most intellectually inspiring and exciting experiences of my life. So I then went off to do my dissertation in political science, which was broadly looking at ideas and norms and how they shape relations among countries, read widely on evolutionary biology and other matters related to complexity thinking, took my 150-page theory chapter to my dissertation committee, and you can guess what happened. Blank, total incomprehension. I was told to take out the 90 pages or so that had anything to do with complexity and evolutionary thinking, and was advised to write a much more standard type of political science dissertation, which I unwisely did. I never published the dissertation. I did publish the 90 pages in one of the top journals. But the experience convinced me not to become an academic. So for the next 10 or 15 years, I was working in the policy world, most recently at Brookings. Since coming to Singapore, however, and especially since joining Singapore Management University a couple of years ago, I have discovered a rich interdisciplinary community of exactly the kind that we have been talking about this morning. And in doing a little bit of background reading on Robert Axelrod's recent work in preparation for chairing this morning, I came across his address to the American Political Science Association, published in 2008, and I could not recommend it more strongly. If you want to be inspired as a researcher, as a thinker, whether you're in political science or in any other field, it is a clarion call to the value of broad thinking and reaching outside your own discipline. I recommend it to all of you in the strongest possible terms. And with that, I would like to introduce Robert Axelrod, who really needs no introduction. Everyone here has probably read Evolution of Cooperation, and if they haven't, they should. But I also hope that you will take a look at his much more recent work. And he tells me that what he's going to present this morning has not been presented before publicly, so we're looking very, very much forward to hearing about the theory of meaning.
Thank you. It's a great honor to be here. This is, Anne said, his new work, and I decided to present it first as far away from home as I could, which I've managed to do here today, and see what your reactions are. And one way of looking at it is I'm taking up Murray's challenge from this morning of doing integrated work on some front, and the front that I have selected could be regarded as a study of coarse graining. As Murray said, one of the major challenges in doing a crude look at the whole is how one does coarse graining. And one can view, as I'll explain at the very end, how what I'm talking about today can be thought of as a effort to understand the tools and needs of coarse graining. I've called it a theory of meaning, and I will give you a specific notion of that in a moment. Another way of looking at it is how a schema reduces complexity. And so I'll explain also what I mean exactly by a schema, but the basic idea here is that I want to talk about how complexity can be reduced and how it often is managed. So let's take an example of one schema called the balance schema, and it's as President Bush once said, you're either with us or against us. That's the kind of perspective that is represented in the balance schema, where friends of friends are friends, friends of enemies are enemies, and enemies of enemies are friends. Another way of putting it is the whole world is divided up into two groups, or maybe just one group. And so, for example, suppose you know that A likes B and B likes C and D likes E, then you can't infer much else except that A likes C. But suppose you know one more thing. Suppose you also know that A does not like D. And so I'm using a dashed line for a negative relationship or dislikes. And once you know that, then with a balanced schema, you can infer all of the other links. And with 5 nodes or countries or people, whatever the nodes will represent for you, there are 10 possible links. So with these 4, you can infer the rest. And so, for example, once you know that A doesn't like D, then you know that E also doesn't like A because it's a friend of D, and then those are all the links that you can infer. And so with a balanced schema, if you know a little bit, you can infer a lot more. So here's a definition of meaning. We could say that the meaning of some news, like this idea that A does not like D, what is the meaning of that? Well, given that you're using a balanced schema, you're seeing the world in this way, and given your prior information, which are those 3 links that I started with, that A likes B, B likes C, and D likes E, if you know that the news of this one further link, given balance in those 3 links, is 6 more things. And those are the other 6 that would make the complete graph. So the definition here of the meaning under the schema of balance is this new information given the old information, and that can be formally defined as the information available from knowing everything among these things, minus what you know just from knowing X and what you know from just knowing Y. It's one of these examples where the whole is greater than the sum of the parts. And so knowing everything would be 10 bits, and X was just 3 bits, these 3 links that you were told. Y is this new piece of information, which is 1 more bit. And so the meaning of Y given X under the balance schema is 6 bits. And this is related to Dr. Gelman and Lloyd's effective complexity, and if anybody asks about it, I'll refer you to Murray. So here's another example of links between countries. I thought you'd be interested in how I see the Pacific Rim. And here, this is not balanced. For example, South Korea really has a lot of problems with Japan, but they both like the United States. So just this triangle alone is not balanced. And there are others that are not balanced. Another thing you could see from this is that they tend to be a hub and spoke pattern to a lot of this, which is very different from Europe, where, for example, Britain, France, Italy, Germany, the United States, and others all have a mutual alliance, but in the Far East, it's more bilateral. I put this one in red. The relationship between China and the United States is basically positive now, but it's under a variety of stresses and will be under more stress in the future. And I personally think that this relationship, whether it stays plus or becomes minus, is the most important event or lack of a change in the next at least 20 years. The world will heavily rely on whether this stays positive or not. Okay, so some definitions. First, I want to describe a state space, which is an abstract term that is widely used in physical sciences, but it basically means everything that's possible is a point. Every different thing that's possible is a point in a space. And in this case, the allowable configurations, by which I mean the different ways that a graph can be, such as that being one configuration. An example would be any graph, or which commonly called networks nowadays. So it's a set of nodes with a positive or negative link between each pair of nodes. So if that's the universe that you're thinking about, then a schema would be any subset of that space. An example of a subset that I've already given you is the balance graphs. Not all graphs are balanced, like we saw, but the balance graphs would be a schema or within this space of graphs with nodes and plus or minus links. So here's another schema, rank order. So you're all familiar with this. If you can think of A greater than B or B greater than A, could be wealthier, richer, stronger, anything like that. And then, of course, it's transitive. If you know that A is stronger than B and B stronger than C, then A is stronger than C. And so one example that's simple enough is if you know it's ABC, and then the meaning of C is bigger than D, is that A and B are also bigger than D. And in fact, you could then summarize that with a simple chain. But another example would be, suppose you know that another three things are ordered that way, but the meaning of the middle one is bigger than some new one, which is illustrated in the graph below, tells you that the first one must be bigger than G, but it doesn't tell you anything about whether the third one, F, is bigger or smaller than G. And so there's a different set of inferences and meanings from a rank order kind of schema than there is from a balanced schema. And there's a lot of uses of a schema. The first is that you can infer missing data. And we've talked a little about that. I'll come back to each of these in sequence. So if you don't know some things, as we saw before, you can infer some of the missing data. You could also correct errors. If you've observed some things that are erroneous, you could actually correct some errors, and I'll show you how. You could also predict what changes are likely to happen in the system. And you can economize on memory in the sense that if you believe things are, for example, balanced, then you could keep track of things with a lot less memory than having to keep track of every pairwise relationship. You could also evaluate source credibility. If some source tells you something that doesn't fit in with everything else you know, you might not trust other things they tell you. You can also measure how much stress there is in the system. How good of a fit is it to that schema? And finally, if there are things that don't fit well, you could focus attention to decide and to kind of resolve the ambiguity that's implied by the way some piece of information doesn't fit into the schema. So for example, starting with missing data, we saw that if you know just 4 of the links, namely the 3 from X and the 1 from Y, you can infer the others. So that's an example of how you could fill in missing data using a schema. You could also do error correction. So an interesting point is that any two balanced graphs, which remember are ways of dividing the nodes into 1 or 2 groups, any balanced graphs have to have at least n-1 links that are different. So why is that? Well, take this example. You have 3 of them in one group and 5 of them in another. And of course, within each group, they're positive links, and between groups, they're negative links by definition of the balanced schema. So suppose that the C moves from the first group to the second. So that would be another balanced graph, but it will require changing all of C's links because it used to like A and B, and now it doesn't. It's in the opposite group, and it used to not like D, E, F, and G, but now it'll have to like those. So for any one change from one balanced graph to another with a single node changing sides, will change n-1 links, namely any one of them with all the others. As a matter of fact, you can prove that if more than one node changes sides, then there'll be at least 7 and probably more links that are changed. So the point here is that these balanced graphs are not very similar to each other. They have to be at least n-1 links apart, where n is the number of nodes. And that allows you to correct errors. So suppose you have, in this case, with n equal 8, you saw that they were 7 apart. So that means you can correct 1, 2, or 3 links. Because if you're 1, 2, or 3 links away from a balanced graph, you'll be further than that away from any other balanced graph, because they're 7 apart. They're at least 7 apart. So if you're less than halfway toward another balanced graph, then you have a uniquely close balanced graph. And that means that you can correct up to half of the distance between graphs, which in this case was 7. So you could correct any 1, 2, or 3 links that are in error when you were measuring the whole thing. So for example, if you had 20 nodes, up to 9 errors could be corrected because there were 19 apart, and anything up to half of 19 then could be corrected. So this gives you one value, one kind of thing beside filling missing data. If you have all the data but some of it's wrong, you could actually correct it, provided there's not too much error in it. Another thing you can do is predict changes under the assumption that's empirical, and it will only apply in certain cases. But if it's the case that an unbalanced graph tends to move to the closest balanced graph, and I'll give you some examples to show you why that might be, With that assumption, then if you can actually predict where it'll go. For example, if you start with this one where there's 2 on one side and 5 on the other, if C likes A but not B, then C has got a problem because it likes one of the people in the left group and not the other. But let's suppose it also likes one of the people in the right group but not the others. Well, that's going to be an unbalanced graph. And there's a prediction about what will happen here, which is this closest balanced graph, is that C will come to like A, because on the left side of the AB group, there's only one problem that C has, namely what its relationship with A is, since we've assumed, I'm sorry, with B, since we've assumed it likes A but not B. And so if it comes to like B, it solved its problem of being in the left group, but then it also has to change its mind about D, which it likes, but now it's in the other group. So just a few changes will make, just 2 changes in this case, will make a balanced graph where C would prefer to join the left side rather than the right. So in this sense, links can be predicted. If it's going to change toward the nearest balanced graph, you could make predictions about how it's going to change. So here's another example. In a couple of years ago, when we had the uprising in Syria, before that, Syria was siding with Iran and with the Syrian regime of Assad. But Israel opposed the Syrian regime, and so it sided with the Syrian opposition when it became dominant. And of course, the Syrian regime and the Syrian opposition didn't like each other. And so you did have, in this case, when the uprising took place in 2011, a balanced situation where Turkey, Iran, and the Assad regime were on one group, and Israel and the Syrian opposition were in another, and there's mutual dislike across the 2 groups. But the next year, things changed, and the changes are in the bolder links. So Turkey came to oppose the Syrian regime because there were lots of conflicts at the border, and the regime Turkey opposed the Syrian regime because there were lots of conflicts at the border, and the Turks came to give refuge to the opposition. And so what tended to happen was that Turkey became hostile to the regime and favorable to the opposition. Now that's also not balanced. For example, Turkey, the Syrian opposition, and Israel, the Syrian opposition being favored by both Turkey and Israel might suggest that Turkey and Israel would come to like each other, and that Turkey and Iran would come to dislike each other. If that happened, it would be balanced again with those 2 changes. And I wrote this slide a week ago, and the very next day, I read in Reuters, despite the widespread belief that the ties between Israel and Turkey are virtually non-existent, in fact, they've been talking to each other, and maybe something will come of that. So that is changed to the closest balanced graph is represented by this, where Turkey and Israel not only would talk to each other, but something would come of it. And of course, there's big barriers because Israel killed 9 Turkish citizens when a ship from Turkey tried to supply Gaza. And Turkey is asking for an apology, but maybe something will work out in that regard, in which case Turkey would probably then break with Iran because Israel is an enemy of Iran. And that would give this a new possibility. So there's an example of a prediction, and as Murray says, don't take it too seriously. But schemas do help you. Another thing that they could do beside prediction is help you economize on your memory. For example, a graph with n nodes has a lot of links. It's n times n minus 1 over 2. How do you know that? Well, for each of the n nodes, there's a link with the others. That's n times n minus 1, but the nodes are assumed to be symmetric. And so if you know whether A likes B, you know whether B likes A, and that's why you divide by 2. So an example would be if you have 8 nodes, you'd have 28 links. We gave you that earlier one with 5, having 10 links. So the point here is that a balanced graph with n nodes only requires n minus 1 links, provided they're connected as they were. Let me see if I go back to this early one. Oh, probably shouldn't have done it. So provided they're connected, you can infer all the rest with n minus 1 links. Okay. So what is the efficiency of this? Well, for example, the first example here is that with n nodes, you only need 7 links, whereas actually there are 28 altogether. So any 7 that are connected, that connect all the nodes, will be sufficient to predict all 28. If, for example, if you have a bigger number like 20, well, then you need 20 links to infer everything, and 190 if you don't have a balanced schema. So by the balanced schema, if it's reliable, will save you 90% of your memory, and that's very efficient. Another thing, as I mentioned, is you could evaluate the source credibility. You could use the error correction method we discussed before to identify what links need changing to get to the nearest balanced graph. And then you could say the people that provided the information about those links might have given you misleading information or wrong information or badly measured things. And so by discounting what they tell you about other things in the future, you might be able to prove your accuracy by knowing which sources to believe and which to doubt. Another one is you could measure the stress in the system. So we could define stress in a graph as the distance to the nearest schema. If it's a 0 distance, there's no stress, and you're already at a balanced graph. If you're 1 link away, then there isn't much stress. And if there's several links away, then there is more. So you could define stress as just the number of links you need to get to the nearest balanced graph. And then you could use stress to evaluate the goodness of fit. How good a fit is, say, a balanced graph to a given set of information, like the Pacific Rim example I showed you. And so a graph might, suppose you have a graph where there's 3 groups of friends, all of whom like each other within their group, and they dislike the other 2 groups. Now, that's not a balanced graph because it fails on the idea that an enemy of an enemy is a friend. If there's only 2 groups, then an enemy of an enemy is a friend. But if there's more than 2, an enemy in one group might be an enemy of a second group and not be a friend of yours. So if you use this a 3-group schema, you could actually have less stress. You might be able to account for the data with fewer errors if it fit a 3-group schema than if it fit a balanced schema. And so you could actually measure the stress in one kind of schema versus another for the same data. And that can lead you to a prediction for a given schema, say going back to balance, that the change will be the change that minimizes stress, that reduces the stress from where you are to the closest place where there's no stress. And you've heard of the maxim that politics makes for strange bedfellows, and that's true. But we have an addition to that idea, which it minimizes the strangeness of bedfellows. That is to say, it actually minimizes the stress and brings together, for example, in a political coalition, the parties that are most similar to each other. So even though there'll be some stress left, because not everybody likes everybody completely because they have different positions, it'll still minimize the stress. And finally, the final use I'm going to mention of using a schema is that it helps you focus attention when there's ambiguity. So if a graph is nearly equidistant between 2 balanced graphs, you can identify which links would need to change to send it one way or the other way. And that would mean that if you wanted to see which way it's likely to go, you might study just those few links that would distinguish the critical experiment of whether it's going to go one way or the other way if they're equally or nearly equally distant from 2 balanced graphs. And that is a major advantage because you don't have to study and closely observe everything. It'll suggest which kinds of information you need to resolve the ambiguity. Now, that brings me to the interesting topic of beliefs and reality. And I would say there's 3 reasons why the world might fit a balanced schema. The first one is that the changes in the world tend to move toward balance. For example, we tend to see things as friends and enemies. And if you think there's only 2 groups, then you'll think that the world will actually move that way because those that don't belong will join the coalition that has the most that they're most similar to or that they would have the least conflict with. And so under certain notions of balance and under certain situations, the world might actually move toward a balanced schema. And in general, it might move toward a particular schema that is appropriate to the situation you're in. I've been using balance for friends and enemies. So one major reason one major issue about schemas in the relation to reality is the world tends to move that way. But a second is people tend to believe it because it's cognitively efficient, as well as because it would tend to make good predictions. And so if you have certain friends and certain enemies, and there's somebody else that you find is a friend of one of your enemies, then you can make all kinds of predictions about them, and you might not trust them, for example. Whereas if they're a friend of a friend, you might trust them. And because of that, we get to number 3, that if you see things this way, they actually could be a self-fulfilling prophecy. Because if you only know that somebody is a friend of an enemy, and then you treat them as an enemy, that would tend to be self-confirming. But if you know they're a friend of a friend and you treat them as a friend, that too can be self-confirming. And so belief in a schema can be self-confirming because these first things, the first idea that the world moves that way, and the second idea that it's cognitively efficient for people to take cognitive shortcuts to think of it that way, both of those reasons can reinforce each other in a self-fulfilling prophecy. And so those are the 3 reasons about the relationship between beliefs and reality about why schemas would tend to be valid. Now, there are various schemas. I've emphasized the balance one, and I've told you about the rank order one. Another example would be multidimensional. For example, a 2-dimensional mileage chart. If we had a mileage chart between cities, then that has a certain structure. For example, the triangle inequality must hold if you're in a flat part of the Earth. And you could have a higher dimension to account for data, such as the scheme we had on the crude look at the whole, which was a multi-dimensional, 2-dimensional view of the similarity relationships among disciplines. Another example, of course, is trees. And tree structure is like an organization chart, one at the top, and then several subordinates, and each subordinate has subordinates. And so a typical hierarchical organization is represented as a tree, and the tree of life is a biological idea, of course, that there's kingdom, phylum, class, order, genus, and species, and those are layers of a hierarchical structure. And hierarchical structures sometimes have what John Holland and others have emphasized are default hierarchies, which are things that every level has inherits the properties of the level above it. So if dogs are an example of mammals, they also inherit the properties of mammals, such as they give live birth. So tree structures are another kind of schema, and there's many others that you can imagine. And these schema differ on which situations the real world they apply to. Obviously, trees don't apply to the same thing that clusters do, and so you need to pay attention to what kind of situations you're dealing with to pick the appropriate schema. But one of the interesting things is they differ on their robustness, and the robustness could be thought of as the basins of attraction. And what I mean by that is the idea that we talked about prediction, that if you're several away from a balanced schema, that balance one, if it's the closest, it tracks the state of the world to the balanced one, and so there's an area around it, graphs that are similar to the balanced graph that are attracted to it, and so the size of the basin of attraction is just the number of unbalanced graphs that will move to a given balanced graph. And that size of that basin of attraction, I'll show you another geometric view of that in a moment. That gives you different properties of different schemas. Now, how do you choose between schemas? Well, here's one a very simple example. Suppose that the cost of choosing a particular schema is the number of incorrect beliefs that you'll get if you use it. And of course, that's what you want to minimize. And suppose you are a Bayesian and you have priors that you think it's probably a balanced schema, but maybe it's a 3-cluster schema. So if those are your priors, then for any given graph that you observe, any full set of relationships, you can actually choose whether the balance, you can actually calculate for the, if it's balanced, how many things have to change. If it's 3-cluster, how many have to change. And since you have those priors, you could actually calculate the minimum, what minimizes the expected cost. And so this gives you one way of thinking about optimal beliefs over schemas. So here's a more complicated example. They're dealing with 17 countries, and I'll show you 5 at the beginning, and then we'll deal with all 17. So the question is, who lined up with whom in World War II in Europe? And before the war, in the late 30s, the basic situation was that Britain disliked communism and the Soviet Union, and it also disliked Germany and Nazis. And Germany disliked the Soviets, and it disliked Britain. And so there's those, the underlying nodes are the major actors, and I'm giving you a couple of others, Poland and Hungary. Germany was aligned with Hungary, and Britain had a defense treaty with Poland, and so it was aligned with Poland. And you could see, just from the heavy-duty lines there, that this is an unbalanced schema. For example, Britain is against the other two major powers, and each of them is against Britain and the other major powers. So that's unbalanced. And what happened first was that in 1939, Hitler and Stalin got together. The Germans and the Soviet Union had a pact, a non-aggression pact, which divided up much of Eastern Europe between them. And then you had this situation, where that negative relationship changed to a positive. Now that's balanced, that Soviet Union, Germany, and Hungary on one side, and Britain and Poland on the other. However, that didn't stick because, well, let's see, this one shows that it's still balanced. Even though these two are aligned, they knew that they still didn't like each other, and so this was kind of a very fragile link, and they both knew it. And then in 1941, of course, Germany invaded the Soviet Union, which made that link negative. And now you have another balance graph. Now, going back, so they asked Churchill, they said, you've been anti-communist, anti-Bolshevik your whole life, and how come you can align with the Soviet Union now? And he said, well, if Hitler invaded hell, I would make at least a favorable reference to the devil in the House of Commons. So this is his notion. Well, yes, I could have a positive link with hell, which is the Soviet Union that he's always said was hell, but he's going to make a favorable reference. So he's going to treat them positively just because it was Germany that got involved. And so Britain did change its mind about dealing with the Soviet Union. This too was balanced, and this is what the rest of the war in Europe was organized around. So let's be more ambitious and actually try to predict the countries taking sides. Now, we don't want to use alliance structures because that kind of begs the question. So I'm going to use the properties of the actors, and I'll show you how I do that. But first of all, there were 17 countries that were involved, and now we know that with 17, there'd be 136 links involved. And there's actually a lot of balanced configurations. Well, how many balanced possibilities are there? Well, for each of the countries, well, let's take Britain to think. If you think about Britain, if you divide all the other 16 into friends and enemies, that'll be a balanced schema. If its friends like its friends and its enemies like its enemies, and the friends of Britain are all enemies of the enemies of Britain, then any way of dividing up the other 16 will give you a unique balanced arrangement. And that's, so it's 2 to the 17 minus 1, which is 65,000. So there's a lot of possibilities to get balanced graphs out of this many nodes. But now, in order to help us make a prediction, let's take into account that countries don't just like or dislike, they have propensities for liking each other that are either positive if they actually have a lot of reasons that they prefer to work together, or negative if they have reasons to work against each other. Now, how are we going to estimate that? Well, there's the way I chose to do it. I took 5 characteristics of a pair of countries, and I used those to decide whether they had a propensity to work together. So one is whether they have a similarity of religion, another one was whether they have a similarity of government type, and others if they fought a war against each other, whether they have ethnic conflict relating to across that border, and whether there's a border issue. Now, most countries don't have any borders, so they don't have issues, but some of them, of course, do. So if you take these 5 things and you don't know better, you just weight them equally. And that's how I got the propensity of any 2 countries to want to work together. For example, the more similar they are and the fewer problems they've had in the past, the more likely they want to align today. And then how about a country's stress? Now we could talk about stress at the individual country level. So if you've arranged things into some tentative arrangement of two sides, then you could take for a given country, let's say Britain, you could take the weighted propensities of the countries that are on its own side in this tentative arrangement and subtract the propensities of the countries on the other side. So ideally, you'd only have positive numbers in this first factor and negative numbers in the second factor, then you'd really be happy. And you want to weight those because Britain cares more about its relations with, let's say, Germany than it does with Luxembourg. And so obviously you want to weight the bigger countries more, and there's a standard way in international relations research to do that using national capability, which includes three factors of the demographic, the population and the industry and the military, standing military. And so when you take these pairwise propensities, you get for any given configuration, you could say that even if it's balanced, it will have a certain amount of stress. Like it might be balanced in the sense that you've grouped people into friends and enemies, but they might be, some of the friends don't like each other, so it would still have stress. And so the premise or the prediction would be that a country will change sides. If it's in some tentative arrangement, it'll change sides to reduce its stress. And this can be regarded as moving from one balance graph to another, presuming when it changes sides, it changes all its linkages with to become positive with the side it's on. So it might not like it, but it'll have these positive relations. So if you start it with a random alignment and then let countries change sides until no one wants to change anymore, then you get to a local minimum. And that'll be the prediction that this approach will make. And here's what you get. Remember that there's 35,000 possibilities, and actually you get only two local minimum. And the first one is the vertical division, where you have these countries against these countries. And that's actually what happened. Britain, France, for example, was on the same side as the Soviet Union against Germany and a bunch of its allies. However, there's another local minimum, which if you get there, nobody wants to change, interestingly enough. And that's this alignment, Britain with Germany against, so this is everybody against the Soviet Union and its friends. And that actually is also a local minimum. If you get there, it won't change. And one way to visualize that is with an energy landscape or stress, where here's the configuration space. Now this, remember, is I'm representing this as two dimensions because that's all I can draw and all I can think about. Maybe I can think about 3 or maybe 4, but it's really a 17-dimensional hypercube. That's what this is down here, but we can imagine this as just each one of these points here is a different balanced graph. And so if you start with a given random arrangement of countries and then give them a chance to switch, they'll switch to one that lowers their stress, and because everything is symmetric, it'll lower the group stress. And then it turns out that with these propensities, based on the empirical measurements I told you about, there's two local minimum. And what are they? Well, the first, this one is this is the second configuration, Soviet Union versus the others. And this one is the Axis versus the Allies, which is what actually happened. Remember, I didn't use any alliances. I just used information about the countries and their relations with each other. And so, and it turns out that the basin of attraction of this one is about 90% of the configurations will, if you start randomly, 90% of the time you'll end up here and only 10% there, which is kind of nice because this is what happened. But this isn't silly. Whoops. I presented this particular work which I was done with Scott Bennett to some business school audience, and they suggested that there was another setting that looked to them a lot like the same one, a lot like the same kind of model, which is the problem of setting standards for Unix. As you know, you use operating system, and there were problems of which version, which would be dominant, and the basic computer companies, both software and hardware, divided up in an alliance to try to impose the standard that they preferred. And we used basically the same ideas. And in fact, we actually got two different alliances that also look like this with two local minimum. And here they are, this group versus that group, or the top versus the bottom. And in the first configuration, only one of these 9 were wrong. Incidentally, Go back here. Here, in this first configuration, 2 out of the 17 were wrong, but the probability that you would get that well by chance is less than 1 in 100. So in fact, it's 1 in 200. And so this is statistically significant prediction, and the same thing actually happened here, that this is also statistically significant. So it's kind of interesting that the same basic approach worked for 2 completely different setups, 2 completely different settings, countries and computer companies. Now here's another kind of application. We've talked about graphs with nodes and links. So here's another one, which is curve fitting. So suppose you see data points like that, and you want to understand it, well, and simplify for to make sense out of it. Well, you might say, well, a straight line looks pretty good, with some noise, of course. But now suppose that this was, you knew now that it was, say, housing construction, and let's forget about let's say these were just typical years and not these actual years when there was a huge dip right here. But let's say this was some period when things were more or less normal. And so now, knowing that it's something that might be growing at an exponential rate, like a few % a year, now you might say, well, this maybe isn't in a line. Maybe it's more of an exponential, although you can't really tell for sure. But it would change which kind of curve that you would prefer to fit. Either normally you'd want to fit a straight line if you could, but if it's something that represents growth over time, you might fit an exponential. And those are, in effect, different kinds of schema. So this should have said housing construction, sorry. And so actually what generated this was that each point is a certain growth over the previous point, where, say, 3% annual growth, and and this is quarterly data, so you divide that by 4. So every point is a little bit multiplied by multiplied by a little over 1 for growth. And then there's also a seasonal component, which boosts the second quarter and decrements the fourth. And now, once I told you that, you could probably say, well, actually, maybe it is seasonal, which you probably couldn't see before. But once you start thinking that maybe it's something like agriculture or housing that might have a seasonal component, then you could probably actually see that it does have a seasonal component. And of course, there's also some randomness in this. So knowing what it's about also helps you decide what kind of schema you want to use to fit it. And there's an interesting relationship between which schema you use. It has a trade-off between getting better goodness of fit and greater efficiency in the sense of cognitive ease. So to go back to the first set of examples, if you use a balance schema to understand alignments of countries, for example, it might not be a very good fit. You could get a better fit if you said there were 3 or 4 clusters, but then you lose some efficiency. It takes more parameters, and you have to remember more things if you're going to fit things to these more complicated clusters. So there's a trade-off between goodness of fit and cognitive efficiency. And the same thing happens in this last one I showed you, where you're picking the curve to use for curve fitting. If you use a linear equation, you won't get as good a fit as if you use a quadratic or a third degree. And likewise, there's a trade-off efficiency. This has fewer parameters to remember than this one and this one. And so in both of these cases of applications of schemas, which schema you pick is affect a choice between goodness of fit and the efficiency. And if you've had a course in algebra, you can do better because, for example, a quadratic equation will have the same goodness of fit, but once you know, have some proficiency with it, it's easier to understand and use. So just to review so far, we have these various things you can do with a schema, and that help you reduce complexity, and you can use it in various ways to correct errors, missing data, and prediction, and so on. So here's a third application. We saw the graphs for alignments and balance schema and related ones, and we saw curve fitting. And here's another one, which is interpreting pictures. So this is a typical problem that artificial intelligence has, which is if you're giving it a picture that a human would understand, how can the computer come to understand what's going on here? And this is a famous example where it's clearly a face, but it's a face which is a very common schema. We're very ready to interpret ambiguous things as faces. But in this case, there are 2 different interpretations of this one drawing in the middle. You could either see it as an old woman looking down and to the left, Or is a young woman looking over her shoulder? Now, can you see both? How many could see the older one, an old woman? And how many could see a young woman? And how many could see both? And how many could see both at the same time? No, that's really hard to do. You might understand both, and you might be able to switch between them, but it's really hard to see them both at the same time. And if you had trouble seeing both of them, this is a slight distortion that emphasizes the older lady, and this is a slight distortion that emphasizes the younger one. And this is like moving from a graph between two different balance schemas, and you can move one way or another way to resolve the ambiguity. But there's a case where the schema of face can be used in two different instantiations. Okay. So we have one more after this. The summary here is that we've seen is that you can use schemas to reduce complexity in the sense of information. I want to be clear that this is I'm using complexity in the sense of information efficiency. And reducing complexity means that you can do better with a schema. And so we saw how this can work for networks of relations, or which are balanced M clusters or rank order. We saw how it could work for curve fitting and interpreting pictures. Now I want to show you how Murray inspired me, and let's see if and how all this relates to what he was talking about, which means that I want to go to a slide I just did over the coffee break, and so pardon any spelling. So Murray recommended doing integrative work on at least one front to get started. I'm not as ambitious as to do all the fronts, but I'll do one. But this talk can be thought of as dealing with one of these integrative issues, which is how do you do coarse graining, which is one of the most important features of taking crude looks at the whole, is how do you do coarse graining. And this approach toward using schemas to simplify the information and to organize it is definitely integrative. For example, as political science, it certainly was about, you could use it to study alignments and conflict, as I showed you. You could think of it as relevant to economics because I did a cost-benefit analysis of choosing schemas, kind of cost-benefit analysis is the heart of economics. It's also about psychology because it dealt with mental models and perception. And anthropology, Murray says we should try to minimize in-group, out-group thinking, but in fact it's there, and this helps us understand at least some of the ideas about why it's cognitively efficient to organize things that way, even though it has unfortunate political consequences. And so it speaks to anthropology about in-group and out-group problems. Philosophy, well, this is a theory that suggests that meaning, which is one of the major philosophical concepts, can be one kind of meaning at least is what is the inferable knowledge that you get. If you know some things and you know what schema to apply and you get some news, what's the meaning of that news? Well, the meaning of that news can be regarded as the additional knowledge that you get by virtue of having that schema in your prior knowledge. Statistics, of course, is about goodness of fit and about the choice of which function to use to represent data. In physics, we actually used here the concepts of stress and energy, and the landscape with the two local minimums is actually a Lyapunov function, which means it always will fall down and not up, and it won't go back or in cycles. Another physics idea. Now, in game theory, if you know what schema the other one's using, you could actually use this to deceive them. Because if you could set it up so it's similar to one of the things that is close to one of their one of their well-formed beliefs, then they could round off the errors that they might observe and decide that the evidence fits a certain schema that you want them to have. And so this is a game theory problem of deception can be used with this schema concept. Artificial intelligence is also dealing with perception, of course, but also the meaning of big data. The major problem is when you have this huge amount of data, like all the Twitter links or something, how do you find meaning in that? How do you find the patterns in that? Well, one way that at least to help is to have some schema to start with and then use these techniques to find the closest exemplar of that particular schema that would fit as well as possible. Now, of course, there's always going to be stress in that fit, but we can talk about how to reduce that stress with different schemas. And finally, for complexity theory, it's one way to think about how to cope with complexity, how to reduce the complexity that we have. So it is integrative, but it's not integrative across everything. But it does, I think, speak to the important question that you want to deal with when you're taking a crude look at the whole, which is how to do coarse graining. Thank you.
Wow, hands are popping up already. Thank you for an absolutely fascinating talk. I think you're going to answer questions from here, right?
Yeah.
So let me start with the hands that I see already, and let me start with Ambassador Chan.
Thank you very much, Professor Axelrod. I'm from the Singapore University of Technology and Design, and I'm with the Lee Kuan Yew Center for Innovative Cities. I told you earlier, I'm a political scientist. I find your schema interesting, but I wonder how applicable or usable it is, because I think it does not take into consideration some of the more interesting developments of late. For instance, the quality of, you have friends and enemies, but maybe the nature of relationships between states these days can fall into the category of neither friend nor enemy, and countries don't want to choose. It is also the end of the Cold War, so to some extent it's a bit of the end of ideology. And even if it is a civilizational conflict, it may not end up in friends or enemies. Also, I think economics now plays a very major role in determining directions of relationships. So when you just take it simply as friends or enemies, it is a bit more complicated. Take, for instance, the relationship between the United States, Australia, and China. Australia is an ally of the United States, but Australia has a very deep economic relationship with China. And Australia really doesn't want to have to choose, you know. And once I said, can an ally have as its largest trading partner, a country that your ally has some problems with? But even there, the United States today says that it really is not an enemy. China is not an enemy, it's just a competitor. So these are more complicating considerations which should be new nuances in how you apply the scheme. I can also think of, the sets of relationship of India, United States, and Iran. Japan, Iran, United States, because the economics comes in, and so when you try to apply sanctions and to get people to follow the sanctions, NDAA is really troublesome. Thank you.
I agree with all of your comments about the real world. And I'd like to say some of those are pretty easy to incorporate into the formulation that I've proposed, and others are not. But for example, if there's an economic neutral gains from trade, that would be one reason why two countries might want to have good relations and overlook some problems that they might otherwise have. And that would be built into the pairwise propensity as one of the factors that would determine whether they want to maintain good relations. So I think you could build economics in the way that you suggested in a straightforward way. Second, there are going to be situations that are neither clear friends nor clear enemies, which is why I moved to this propensity idea that there's a degree of willingness to cooperate versus taking a zero-sum orientation, and that you could actually take that into account. So for simplicity, I drew dotted lines or solid lines, but I also showed you how you can think of those as real numbers, plus or minus. Now, I grant you that even that is oversimplification, that you could put these various factors into a single scale. But on the other hand, it might be useful as a crude look at the whole to think about if you do put these various factors. And then you could actually see some of the problems that you're pointing out, which would reflect the stress in the system, so that if the United States has kind of a mixed relation with China, to take your first example, but Australia wants to have good relations with both the United States and China, then to the extent that the United States and China are competitive and start saying nasty things to each other or mobilizing their military, their navies against each other, to that extent, it's going to be unbalanced, and Australia is going to have some stress in maintaining a very cooperative relationship with both sides if they're not getting along with each other, and that's exactly what I wanted to show. So I think that some of these issues can be dealt with as measurement problems, and some of them are just reflections of the stress that's in the system. And still others, this kind of simplified scheme won't work at all for, but that's what you would expect from a crude look at anything in particular, such as how to do coarse graining.
Quite a few more questions. Just one comment. My initial reaction was exactly the same as Heng Chi's, and then I started thinking about what's the scope to which the balanced schemas would apply. The situations you were talking about were situations of declarations of war and peace, crisis decision-making, where this kind of simplification down to friend and enemy does happen. The literature shows that very clearly. But then I also started thinking about the partisan polarization happening now in the United States, where people seem to be grouping themselves in exactly the way that you're describing, in the absence of that kind of crisis pressure of decision-making. So I think I want to give more thought to how widely this applies. Please.
So when you talked at the beginning about the example of Iran, Syria, Turkey, and Israel, or any of the other examples, you deliberately simplified by ignoring the fact that they're all parts of bigger networks, like involving the United States. And so the first question is, if you have, at the broad scale, a network that's unbalanced, or that's got high degrees of stress in your second approach to the problem, what can you say about the subgraphs? For example, what's the maximal number of balanced subgraphs you could have of a degree K in a larger graph that's unstable? And secondly, can you say anything about how the stress or the unbalanced nature will be resolved in terms of will it be the subnetwork that would cause the greatest change in the direction you want? What is there some hierarchy theory that allows you to go from the larger networks down to the components?
Those are good questions. The first one about how many ways... Is it off? The first one about how many ways you could have subgraphs that are balanced, that you could actually do mathematically. I couldn't do it in my head, but you could actually say if there's 17 nodes, how many triangles could be balanced without the whole thing being balanced. That's a knowable question. On the first one about resolution, suppose you had different clusters of balances, but then the various subsystems are interacting with each other. Can you predict what's going to happen? And I think you could, and the way you would expect it to happen is that some of those subclusters will merge with each other, and until, if you want to assume that it's going to be balanced in the end, then obviously you're going to have some of these subclusters. The most likely thing that will happen is that the final two sides will consist of subclusters on one side, some of the subclusters on one group, and some of the subclusters on the other. And so that you would have the emergent property that these subclusters are going to emerge according to their probably some aggregate propensity between those subgroups. And so the two subgroups that really hated each other were less likely to work together than two subgroups that were indifferent to each other. And so I think that you can use this to study emergence from subgraphs to a unified graph, and if you took the larger system into account. Now again, this is meant to be a study of how one can do coarse graining, but it's not really claims to take into account to be a full theory of conflict, for example. But we did see that you can make some predictions that work not only for countries but for companies. And so it probably does have some validity. And so I think you can study emergence of something.
And presumably these transients, their data for make this testable. I'm wondering also if there's a link here or parallel you see to Duverger's theorem.
So you want to state it for us?
Oh, I mean the theorem, which I thought was a political science theorem.
It is.
That
I could state it too, but I'll let you.
that within political systems like the U.S., you won't long have more than two political parties.
Right.
It seems to me that your approach to resolving the balanced graph thing would give you this as a prediction.
Well, I don't think so, and I'll tell you why. I think the Duverger theorem comes from the idea that the American electoral system says that whichever party gets a plurality of the vote, like if it's 40, 30, 30, then the 40 becomes the president. And therefore, there's no point in supporting the weakest of three parties, and therefore you'll tend to move to only a two-party system. And that's a function of the way you count the votes. In many other democracies, in fact, most of them, there's proportional representation. And what you do then is you give the number of seats in Parliament in proportion to the votes they got, and then in Parliament, there's bargaining over which group will get together to form the cabinet. And that, I think, does correspond to this idea that the cabinet, that the coalition that gets together will minimize the strangeness of the parties working together. And therefore, when you get the ins and the outs, in that case, the reason I don't think it's permanent is because in the next election, there could be a different distribution and a different movement in the ideological space. And so Duverger is really about the consequences of having a plurality electoral system. Most democracies have the proportional, which can keep the diversity at the party level. But then at after each election, there'll be a bargaining which will, in fact, bring some together. And they might not like each other, but but what the prediction would be is that the ones that get together were the ones that least dislike each other.
I'm sorry, there's quite a few hands going on. I think I saw yours first, and then I'll go to this side of the room and come back to you.
Greg Fisher from the think tank Synthesis. I saw one of the charts had a balanced graph with Germany and the Soviet Union having a friendly relationship, but then the Germany invaded the Soviet Union. Can you explain, kind of in your sort of theoretical framework, kind of how that happened?
Well, we could do it at two levels, of course. I could do it sort of as a political scientist and historically, and give you, which the short version, of course, is that it was convenient for the two of them to get together in a temporary way and divide up Eastern Europe while both of them were arming themselves to the teeth, and they both expected that there would eventually be a war. And the interpretation in the graphical sense would be that they actually still had very hostile propensities. But for the time being, they both had an advantage to work together against Britain. And so they did that as a temporary basis. And of course, it not surprisingly broke down. And the more surprising thing would probably be that Stalin was quite surprised when it broke down. But he wasn't surprised that it would break down. He knew that there were underlying propensities to have a showdown between communism and Nazi governments. He was only surprised that it happened when it did.
Forgive me if I've misinterpreted you, but I thought the idea was if there's a balanced graph, there wouldn't be a change.
Well, yes, and so that would be a falsification of the theory right there. But I would say that it's not a dramatic falsification because if you measured the propensities, what was a positive relationship was about as weak a positive relationship as you can get. And so when it breaks, it wouldn't be very surprising.
Let me turn to this side of the room and in the back, and then I'll come down to the front.
And
Good afternoon. I'm Kaixi from Nanyang Technological University. I have pointed out two possible limitations of this theory. The first one is that the scheme actually predicts how the relationship between the different variables, countries will change after some variable happens. For example, the relationship between these two countries gets sour. So is there any way we can incorporate these changes in the variables also into our scheme, so we don't just do some post hoc prediction, but rather we can predict next time what kind of variables, how the variables will change. The other question is there any way we can incorporate time into this scheme? Because the scheme seems to presume that the relationship between the countries will always tend towards a peaceful relationship. Be the premises that all the countries can become friends, but they cannot all be enemies, or the propensity to go towards lower stress. They all predict that the countries actually want to become peaceful. But the countries won't become peaceful immediately. There may be a time period where there's a lot of conflicts. But in the long run, maybe the countries will tend towards peace. So if we predict that countries will always tend towards peace at any point of time, we might encounter some problems. So is there any way we can incorporate the time scope into the scheme as well? Thank you.
Thanks for those questions. The first one is, if there's a change in one of the variables, can you predict a change at the system level? And the answer is yes. And to take a specific example that, based on what I showed you, that was based on 1936 data about military capacities and other things. And at that time, as you might expect, Poland was hostile to both Germany and the Soviet Union. It was caught between them, not only geographically, but politically was hostile to both. However, in 1936, the Soviet Union was somewhat stronger than Germany, which was rearming quickly. But by 1936, the capacity of the Soviet Union looked bigger. And so Poland, being negative to both, would have been predicted to be more hostile to the Soviet Union, because it was the bigger, more important one as far as it was concerned. However, by 1938, after Germany had continued its very fast mobilization and the Soviet Union had slower industrialization and mobilization, then Germany became the stronger one, and Poland would be predicted to be anti-German. Or another way of putting it, that Germany would invade first rather than the Soviet Union. So when a variable changes, like in this case, the weights on the size of the country, in effect, the weights on their military capacity, as well as, in that case, but you're also taking into account industrial capacity and demographics, but the military capacity is what changed fastest. So when that changes, you can make a different prediction about how the countries will align based on their propensities, which are weighted by that. So that's an example of how if one of the parameters, in this case, the relative strength of the Soviet Union and Germany changes, you can make a different prediction about, say, how Poland will react. So you can do that with any of the variables. The other one was about predicting change. And certainly you can do that, and you could be wrong, and any good theory has got to be falsifiable, and so it's going to be wrong sometimes, and the cruder it is and the more ambitious it is and what it's about, the more it's going to be wrong, and so one doesn't have to be too embarrassed by that. But it's much, much, much better than chance, so that's good. Now, that's what we in the social sciences use as our standard. And then you ask, well, what about, is there a possibility of moving toward peace between all countries? And let me just be clear that while I usually talked about balance as having divided into two groups, also everybody in one group, everybody's friends with everybody, is also consistent with balance. If everybody is friends with everybody else, then nobody has to change, and it is balanced. So a balanced graph could either be actually two clusters or one. And so if the relationships become positive, for example, if economic mutual gains from trade dominate concerns about competitive security, then one could imagine in the distant future that most important relationships between countries, and maybe almost all of them, would be positive. And in some areas like scientific cooperation, that's not so far from what it is. And so the possibility of pairwise propensities being positive, and therefore having one large group, is consistent with the theory if the pairwise propensities lead in that direction.
There were hands over here, and then I'll come down this way.
think I'm adding now anything, but building upon the question already asked to you, I'll take you away from the real world and ask you that, we know something called Arrow's impossibility theorem. And in some sense, you are having this pairwise things with a single issue, but where friendship, enmity can be boiled down to a single, scale variable. We can easily rank pair them and think about stable coalitions and things like this. But in a multi-issue world, where I consider one country as a friend as a friend point and one as an enemy point, like she raised, the group contraction lemma and the field expansion lemma kind of prohibits any aggregation and any conclusion about stable coalitions, which is, in some sense, I'm saying is Arrow's impossibility theorem in a very simple, my understanding language. So is it really possible? I mean, at points, one single issue dominates others. It becomes so important, like Syrian crisis right now, probably dictating the neighbors. But we have seen strange coalitions like United States and Saudi Arabia and things like this, which is, again, probably a single point driven things. But in a multi-issue world, one I'm friend to somebody and one I'm enemy to somebody is what's quite common. And then probably this kind of aggregation, this kind of coalition formation might be difficult to say. I'm just trying to clarify from you.
I'm not sure I follow what the question was.
The question is that in a multi-dimensional issue,
I'm sorry?
in a multi-issue in a
Yes.
world, like where I like A, B,
Right.
C, D,
Oh, okay.
I put points on A, B, C, Ds.
Right. I
It
see
might,
what yeah. Well, if there's one issue, for example, in domestic politics, there's often an important dimension of left-right. And then parties in a parliamentary system will be arrayed on that dimension. And one would expect that the coalition that can achieve a majority would be a connected coalition in that space and have the minimum range in order to achieve a majority. So the same kind of thinking can get you the idea of what it takes. Now, if there are multiple dimensions, there may be multiple ways. If you scatter the parties in two dimensions, some of them might be international and some domestically oriented, for example, as well as left-right, and then you can also imagine which collection of parties will have the least conflict of interest between them, which is to say are closest to each other in a way that how can you get the least stress. Well, put it this way. The prediction you would get is that the coalition that forms is the one with the least stress and still has a majority. So it would be the parties that are basically close together but enough of them so that they do have a working majority. And so that's what you would expect in that kind of system. Occasionally, you get the interesting idea that the outs, who might typically be on the left and right extreme, then that isn't balanced in the sense they usually don't like each other at all. And they usually are even more opposed to each other than they are to the middle coalition that might have formed. And so that expectation would not necessarily be a balanced scheme. It would probably be three groups, the left, center, and right, and you most typically will get a group that excludes both of the extremes, at least some of both the extremes, to form a group that has a majority. And so there you would have you tend to imagine a three cluster where the various left parties that are left out tend to not to be too different, and the various right parties that are left out tend not to be too different. So that if you're doing an electoral coalition situation, your three cluster would probably be the best interpretation.
We have very little time left, so I'm going to take just a couple of questions from people who've had their hands up for quite a while, and then I'm sure Dr. Axelrod will be able to talk with people over the breaks. So Sunil, and then you have the last word.
But in the context of your framework, you mean that the links between two nodes is classified as either friendly or enmity. Is there some way of introducing a metric of intensity and making that metric time dependent? Because then you could look at the fragility of existing relationships as say, time evolves.
Well, I already provided one metric in the example from the European system where there were 5 different aspects that would go into the measurement of whether a given 2 countries would have a positive or negative propensity. They're similar to religion and government and border conflict, ethnic conflict, and previous wars. So those are the 5, and putting those together gives you a metric about how each pair of countries are positive or negative related to each other. And as I mentioned, that is time dependent. In other words, for example, if the countries are mobilizing throughout the 30s at different rates, then you could do that kind of analysis once each year, which I did. And you could see how the fact that Germany was mobilizing faster than anybody throughout the late 30s changed the propensities to somewhat, especially because countries that dislike others would worry more about working with friends against Germany than they would against Soviet Union if Germany was growing faster. So you can definitely get that both metric and time dependency in it.
What I like to do is to actually go from a crude look at the whole to a very precise look at a small part. So actually fine graining rather than coarse graining. So there's been a lot of studies in social networks, right? Tremendous amount of studies where we have data much more than we have on countries actually.
Yeah.
And there's been a lot of studies on how opinion spreads to social societies and how one individual, depending on how you look at that individual, might be part of at least 10 or 20 different subnets.
Right.
And so people can be part of a balanced and a non-balanced net at the same time, if you like. So then I don't understand anymore, how I can use your theory there to understand, for instance, the percolation of opinions. So that's point one. So that's let's say at the same time having being balanced and non-balanced at the same time, and that then is dynamically changing. And the second thing is that there's a thing that we actually discovered ourselves, which is called stochastic resonance in these networks, where there's noise in these networks, and that will actually move you from one minimum to another minimum, and without any, you cannot actually determine where you're going to go. So my question is, does it still hold for these systems? Because it should hold for these systems when you actually take a crude look then. So when you zoom out.
I didn't have time, but I'll use it to just give you a couple of minutes on the time scales of the dynamics, which is your second part. So this is an egg carton, which is meant to illustrate the idea that there are many basins of attraction. I showed you the graph with 2, and this is a lot. Now, again, it's a multidimensional space, not just 2. But suppose the system is where the blue line is. So at a very short time scale, if you measure it once and then measure it very quickly after that, not much would change. And so the short time scale you'd expect to be just where you observed it. But a little later, you would expect it to be moving toward the nearest balanced graph. And if you allow more time, it might get to the bottom of that local basin. But this is the point that you were making, that over a longer time scale with noise, and the noise is shaking the system, it might shake off into a different basin. And then it might be there, or later it might be here. And so over a very long time scale, you can't predict where it'll be, except that it'll probably be near one of the local optimum. And that's one reason why long predictions when there's noise becomes less and less feasible. But it is a emergent property of this kind of thinking. It's not built into it that the longer time scales have a more diffuse predictive ability. But it's more specific than that because it doesn't say you'll be anywhere. It'll say that you'll be close to an attractor.
With that, I'm very sorry to have to say that we are out of time, and since lunch is next, we probably don't want to run over too much. But I would like, before we end, to indulge in the Asian custom of thanking our speaker with a gift. So from one American to another American by way of Asia.